Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. And we're going to talk about inductors this time. This question is from Jim, and he's KD8PGK. And he says, I'm thinking about building a tuner and a matching system. Can a ferrite transformer have multiple ratios, like 1-to-1, 2-to-1, 4-to-1, 9-to-1, etc.? This would be dependent on winding and size. If added to the LC circuit, that's inductor capacitor circuit, in the transformer, would it self-select the lowest impedance on its own? Or would many single ratio transformers in series do the same thing? There's no self-selection when you're talking about inductors. It's either in or out. Now, if you add some intelligence to the circuit, then maybe, you'd have a little relay switch in there and be able to switch in different values, which is kind of how a antenna tuner works. Antenna tuners, the expensive ones, have what are called roller inductors. A big roll, and it's the coil on there, and you turn a dial over here, and it moves the connection point back and forth. Those are called roller inductors. You choose the value of inductance you want. In the less expensive, which is most antenna tuners, they just have an inductor that's tapped at several points so that you can use it by selecting the correct tap. All the antenna tuners I've ever had have that, but the real high-power tuners often may have a roller inductor on the manual. Okay? I want to show you a toroid, what the thing looks like. If you look way down here, this right here is a toroidal ferrite core that has wire wrapped around it. This is a toroid core inductor. Now, right here, this big nasty thing right here, this is the 40-meter version of their radio. This actually has 4 turns on it. It has the main and then 3 little ones. Okay, the main and 3 little ones. This is actually a transformer around a toroid core. Some people shy away from winding these things in kits. It's not that hard. You just thread it like you thread a needle, except you do it over and over again until you get all of the windings in. Every time a winding goes through the core, that counts as 1 turn. Okay? So let's draw a picture here. Okay, now in diagrams, an air core between the 2 inductors, usually you put these 2 together. Very often you will put you'll see this little dot up at the top of the windings, meaning that when this goes positive, this goes positive. Okay. Now, toroid cores have a core. It used to be that all transformers were made in such a way that they had this sort of, that's actually what they look like. But nowadays, they're wound around toroids. So you get winding, 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 and so on. And it's the equivalent of what you're seeing right there. Now, let's suppose that there's 2 ways of doing this. Let's do it the standard way. Let's take a ring, a toroid, okay, and we're going to put a primary winding in here. This is the energy in. Okay, 5 windings, and then it'll come back out, and we'll mark that positive. This is the primary. Now, this is 5 turns. So if I were to wind something over here, the top comes out last. It goes underneath first, and it's got to be in the same direction. So this is a 5 to 2. Okay? Notice these are completely separate. When you do a ballon, you often will completely separate the 2. And you can put another winding in over here, by the way, the dots there. You can put another winding in over here, and let's say that's now 3. So you got 5 to 3, 5 to 2, and so on. The turns ratio equals the voltage ratio. So 50, and this has got to be AC, of course, 50 volts AC, you'll get 20 VAC and 30 VAC, okay? It's proportional to the windings. Now, in terms of impedance, you've got to square these voltage ratings because you're dealing with current also. Now, let me show you another way of doing this, or you're going to see fairly frequently. Let's do our toroid here, okay? And we're going to bring this under 1, 2, 3, 4. Okay, so there's 4 turns, one coming out top. Now connected to this goes underneath again, 2, 3, okay, and the dot will actually be there. This is an auto transformer. Okay, this was 1, 2, 3, 4 turns, and this is 1, 2, 3. So the total number of turns from here to here is 7. So if you were to connect this to ground, and over here you got this coming here, this is the equivalent of 7 turns. And you've got this one connected out over here too. This is called an auto transformer. And you see a lot of balance do that. And the way they work is balance. I'll show you. There's a secret. You've got a winding coming in, and now it goes under. So you have 1, 2, 3, 4, say. And that goes out. This is the common. Now you have another core coming here, and I'm not going to try and keep track of which direction they're going, but that's 4, 5, 6, 7. And you attach the midpoint to ground. The midpoint comes down here and is connected to ground. So this plus this end down here, these 2 windings, this midpoint is connected to ground. This is balanced, and this is unbalanced. Okay, and there are lots of different ways that you can do this. All right? And that way, this is balanced because ground's in the middle. This is unbalanced because ground's on one side. So this is how they work too. Now, to really answer your question, I'm going to need to just add some turns. Let's take this as your primary income, and we'll do 1, 2, 3, and then back out. And this is common at HF, about 3 turns. Now, if you want to turn this into, oh, by the way, if you short this one to, or you bring this down to ground, and you bring another winding down to ground, you actually get an unun. But we'll just do this as several windings. Here's 1, 2, 3, 4, 5, 6. And then it comes out that way. Okay, so there's 6 turns here, 3 turns here. And let's do this one right here that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then it comes out from underneath there. So there's 12 turns. 3 turns, 6 turns, 12 turns. So this one right here has a 12 to 3 or 4 to 1 voltage ratio or 16 to 1 impedance ratio. This one right here has a 2 to 1 voltage ratio or 4 to 1 impedance ratio. If you connect this directly to this, you have a nice tap there if you need it, but now we've got 18 turns, 3 to 18. Okay, so that is a 6 to 1 ratio. 6 to 1 ratio, or 36 to 1 impedance ratio. Okay, so coils add. If you take a coil, now this is the schematic representation. The impedance from here to here, it adds L1 plus L2 plus L3 is the total impedance, L total. This is the opposite of capacitors, okay? They add. Now, if you put coils in parallel, you get a different formula. We won't worry much about that. But if you do have coils in parallel, they will add. If you have a coil and parallel to a coil, it's L1, L2, L3. Each of these are in henries after a famous scientist. Well, I guess normally we would do that these days. It's a name, actually, henries. The formula is 1 over L1 plus 1 over L2 plus 1 over L3. So you got to invert these three, add that, and then invert it again, and you get your L total. It works exactly the opposite with capacitors. Let's go ahead and do that so we keep our capacitors straight. If you put capacitors in parallel, like that, it's kind of obvious. Capacitors, you've got an area, two areas separated by dielectric. Well, you're just adding to the area. So C total equals C1 plus C2 plus C3. Okay, this is parallel. Now, when we did that with coils, it was like series, okay? And you can imagine that if we were now to put these in series, it's 1 over C1, 3, plus 1 over C2 plus 1 over C3. Now, there's a shortcut for this if you've just got 2. It's C1, C2 over C1 plus C2. That's just a simplification of the original C total. You can do a similar one for coils in parallel. Okay, so that gives you a little basic instruction on how inductors add and work together. Coils and capacitors are kind of interesting because in real life there's many different types. Now, like I showed you on this little radio here, this, by the way, is a QRP Labs QCX radio. And coils are just a part of it. They're often on ferrite cores, usually are in radios. You can get all different kinds of ferrite cores. Now, a couple things you need to watch out for in inductors. One is a little bit of hysteresis. Hysteresis, when it takes a moment to start swinging, it takes a little moment to swing back. Okay. The other thing that happens is that the core can saturate. Different cores saturate at different points. You can even saturate an air core inductor. Now, what happens when you do that? Well, you get all sorts of nonlinear effects. Now, what happens with capacitors? With capacitors, the big problem with exceeding the voltage rating is shooting an arc right through the dielectric. That ruins the capacitor, of course, and you get unpredictable results coming out of that. So capacitors are rated not only for their capacitance, but also for their voltage, maximum voltage. Now, another thing with both coils and capacitors is that dielectric materials are somewhat nonlinear, in that as the frequency goes up, the property of the dielectric changes a little bit, okay? So that means that as you go up in frequency with a capacitor, the actual capacitance will start to taper off, and then it will swap, and beyond that frequency actually behave as though it's an inductor, and vice versa with the coils too. So in the real world, you have to be careful of these things. Now, another thing that's particularly important with capacitors, but can be important with inductors too, is temperature coefficient. And this is a real problem when you have a radio. This one right here is based on a crystal and digital techniques to get the right frequency and does very well. But older variable frequency oscillators for HF equipment used to have a whole string of capacitors in parallel. And the reason for that was not just to sell capacitors, although I'm sure there must have been part of it, but each capacitor had a different temperature coefficient. Mostly when the temperature goes up, it makes the dielectric swell, and so the capacitance goes down because the plates are further apart. But there are other capacitors with a positive temperature coefficient. As they get hotter, the capacitance goes up. So if you put these in parallel with each other, it's possible to get a capacitance set for an oscillator to be pretty stable with temperature. Now, usually, I don't know, you've probably seen this with some older radios. They drift after you turn them on. They drift. And so you'll turn a radio on and the frequency will drift. This is very common with the older radios. The rule of thumb was leave it on for half an hour. I had a little MFJ QRP rig, all transistor, had some capacitors in there, and the thing would drift for the better part of a day. And it would be annoying because you'd end up chasing the other frequency up and down the band. The thing to do with that, if you have an old QRP rig that does this, is leave your transmitter where it is and then use the receiver incremental tuning to find the other station and keep the other station tuned in. Because if you change your transmit, then he'll start trying to follow you and you can walk right up the band. So that's just practical considerations for inductors and coils. Now, what do you see in radios today? Little tiny coils are made that are put right on here. You can actually get them where they are surface mounted, and you can get little tiny capacitors. They have very, very low voltage. Now, if you look in your computer, in the power supply are some physically very large capacitors that have a whale of a lot of capacitance. And the reason for them is so that they provide a very stiff power supply. Now, to get that much capacitance, you need to keep lowering the maximum voltage to about 15 volts. So it won't blow at 12 volts, but it will at 15. That way you can get max capacitance per unit area. Okay, I have a box up here full of electrolytic capacitors that only handle about 15 volts each. They're good for circuits that do 5 volts. That's fine. They'll operate forever. Now, electrolytic capacitors is kind of dielectric that is a paste. And you put it on top of aluminum, put the paste in there, put another layer of aluminum, and usually roll it up. Okay? And then you have to give it an initial charge to determine the polarity of the capacitor. If you do it wrong, you'll get it reverse polarity and then it'll blow on you. So you don't want to do that. Some people think it's a lot of fun to blow up capacitors. I'm sure it must be, but remember that what's inside, that electric, is not a product fit for human consumption. Okay, so be careful with that. Plus, capacitors, perfectly good capacitor, has a right to live in a good electronic circuit. So why destroy it? So there you go. We've had quite a little discussion about inductors and capacitors here. And so I'm going to ask Teagan, my assistant, to put this in the ham radio basics section. And we can do lots of things, because what's interesting is when you play with time constants, how they compare with frequency, and you can put a capacitor and an inductor together and it becomes resonant. So there you have it. Until we next meet, 73.